This week we're going to pull some soundings and look at ways that we can identify a lapse rate programmatically. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week I wanted to look at a quick and easy way to calculate lapse rates so we can identify temperature inversions in our soundings. Also, there's some unit tricks that we're going to have to do in here to make everything work. But first, of course, we need imports. Import NumPy as NP because we're programmers that don't like to type long things. Matplotlib.pyplot as PLT. MetPy.calc as mpcalc. From datetime, I'm going to import the datetime object. From scipy.signal, we're going to import the moving median filter, medfilt. From metpy.plots, I'm going to import the sqt object. From metpy.units, I'm going to import the units registry and the pandas data frame to unit arrays helper. And finally, from siphon.simplewebservice.wyoming, I'm going to import the Wyoming upper air object. So quite the list of imports to do this. Oh, and that is pandas data frame to unit arrays. There we go. So first, we need a station to get our data from. We're going to use January 16th, 12Z sounding 2021 at the station TBW. This has a pretty pronounced temperature inversion. We're going to use the Wyoming upper air object, the request data method on our date and station. Then that data frame, we're going to use the pandas data frame to unit arrays helper to attach units to that. And let's make a quick dirty plot here. So I'm going to plot height. And I'm going to plot temperature. This is not how we're used to looking at things, degrees Celsius and meters on the X, but we can see that temperature is going down, 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 and then about 3,000 meters or so, we have this very big inversion, about 10 degrees Celsius inversion here. And there's some other minor little steps, but this is the main low-level inversion that we're interested in being able to identify. So how could we do that? There are, of course, several ways, and change point detection is a whole field of study, but we're going to do some of the more straightforward ways. So first off, I'm going to calculate the lapse rate using metpy.calc, or mpcalc as we imported it, the first derivative function. This is really nice because your data do not have to be regularly spaced, unlike many other derivative implementations. So we're going to take the derivative of temperature, and x is our height, because I want a lapse rate not in terms of pressure, but in terms of degrees Celsius per 1,000 feet. Now, 1,000 feet is a little bit of a weird unit, but that is something that we encounter very often in U.S. meteorology. So let's see what we get just by calling the first derivative. We see we've got some very small values, and if we go look, Kelvin per meter is our unit, which is not really what we want. So in this case, I'm going to do some reassigning and some unit conversion. So we can call the .to method. And unfortunately, I want to go to degrees Celsius per 1,000 feet, as that's a common unit here. But you can't say per 1,000 feet. That does not work. We have to use the standard prefix for 1,000, or kilo, and then our unit. So degrees Celsius per kilofeet. And if we look at that, now we have numbers that look more like lapse rates we're used to looking at, and we have a delta degree Celsius per kilofoot unit, which makes sense. So now let's make a plot of our lapse rate. I'm going to put it on the X, and I'm going to put pressure on the Y. So not really a skew T, but something that might be a little more familiar looking to us. And I'm going to label that as raw data. Okay, we see it right at the surface. We get a rapid drop in those first couple data points, edge effects from our derivative. Then this must be our temperature inversion right here, just a little above 800 millibars. And that indeed is it. We see this 15 degree Celsius per 1,000 foot lapse rate here. And everywhere else we're seeing something in the neighborhood of -2.5 and -3, -2.5, somewhere in there is about what we would expect for our standard adiabatic lapse rate. But what about smoothing this out? We see a lot of jumps and jagged points in here. Can we smooth this and do any better? Well, let's try applying a moving median filter whose purpose is to de-spike data to our temperature before we take our derivative. So to do that, I'm going to add a couple of cells here. Our lapse rate. I'm going to do a 3-point smoothing here. MP calc first derivative. I'm going to median filter my temperature data with a 3-point filter. X is still our height. And we need to take the magnitude of that because the units are going to get a little bit confused here, unfortunately. Multiply by 1,000. That gets us our degrees per 1,000 feet. But remember, we don't have any units now. We want units, so we're going to reattach units of delta deg C per kilofoot. Just a little bit different way to write that. Now I'm going to copy and paste. We're going to do a 5-point smoothing as well, just for comparison. Okay, we have a unit stripped warning, but we're taking care of that. And now let's do some plotting. Lapse rate 3 smooth. And this is a 3-point smooth. We will do the same thing for 5 points. And it looks like the 3 and the 5 are very similar. I'm going to make the 5 a little bit transparent. And yeah, so when we do the smoothing, we see that we preserve the general shape of things, but we really exaggerated this lapse rate for our inversion. So it'd make it even easier to find using just, say, a simple threshold of anything over so many degrees Celsius per 1,000 feet. So you can do some tricks with smoothing and signal processing if you're having trouble picking your temperature inversion out, or there are more sophisticated things that we can look at. But really just looking at the lapse rate and finding high lapse rates compared to the background has done a pretty good job already. I hope that you found this useful, and I'll see you on next week's MetPy Monday.